We are honored to have with us Dr. Gayatri Devi, Associate Professor at Coimbatore Institute of Technology. With over 16 years of academic experience in computer science and a strong background in advanced technologies, Dr. Devi brings deep expertise and clarity in breaking down complex quantum concepts. Thank you, ma'am, for joining us today. We look forward to your insights. Over to you, ma'am.
Thank you.
Okay.
Okay.
Yeah. Ma'am, can you share a journey in, like how, so that people from other background, they can also. Yeah.
Yes. I started quantum computing during this lockdown period. Okay. In 2020, we have some. We are working in IBM Qiskit localization project. My team head is Dr. Manjula Gandhi ma'am, Associate Professor, Department of Computing, CIT. So He's, she is also a mentor for my quantum journey. Okay, so she always encouraged me to learn quantum. But my PhD area is not a quantum computing; it is a ad hoc network routing area. So I accidentally come to this field. I regularly attend this quantum summer school and also quantum challenges, and also I completed this uh, quantum developer certificate in 2023, and also I applied for this Qiskit advocate post. I got it. Okay. I also attended Humanium AI program. I completed Q bronze, Q nickel diplomas. Okay. And also I completed Q course 501 from QWorld. Mm. Okay, and also,
Yeah.
so today's agenda is introduction to quantum computing and single qubit gates and multi-qubit gates. Then we move to Bell states and ZZ states. Okay. So you already aware of this, what is quantum computing and what is the difference between classical computing and quantum computing. Okay, if a computer follows a quantum mechanics, then it comes under quantum computer. Okay, so it operates on 0 1 as well as 0 and 1, both 0 and 1 at the same time. Okay. So we have a group of qubits instead of bits in quantum computing. Okay. In classical bits, we have a bits. In quantum computing, we have a qubits for writing the information. So this is the difference, bit and qubits. We have a zero and one in classical computing. In quantum computing, we have 0, 1 as well as both 0 and 1 at the same time. Okay. So we have many difference between quantum computing and classical computing. Okay. So we in quantum computing we do the calculation with the qubits, which can be represented as a 0 and 1 and both 0 and 1 at same time. In classical computing, we do the calculation with the transistors, which represents either 0 or 1. Okay. So in quantum computing, we have exponential power. Okay. So in classical computing, the power increases in 1:1 ratio. Okay. So this is based on the number of transistors in that classical machine. Okay. So in quantum computer have high error rates, but in classical computing we have a minimal error. Okay. So for a quantum computing we need a special setup. but for a classical computer we don't need. Okay. So these are the some disadvantage of quantum computing. Quantum computer, they are prone to errors, multiple iteration needed for a complete single operation, single problem. Then algorithm creation is very difficult in this quantum computing, and also it needs some low temperature for environment. So it is not open for the public. It is only available in the labs. Okay. So this some linear algebra review. You already know that the notation of quantum computing. We have a Bra notation and Ket notation. Bra represents the row vector and Ket represents the column vector. Okay. So this and also we have a inner product of Bra and Ket vectors, and we have a tensor product of Bra and Ket vectors. Okay. And then we have a complex conjugate in this quantum computations. So if I have a z equal to a plus bi, then complex conjugate of this one is you have to simply modify the sign of complex number in the complex conjugate. Okay. So the Ket vector is represented like this, column vector, C1, C2 up to Cn. Okay. So the Bra vector is row vector, but it takes the conjugate of this column vector, C1 conjugate, C2 conjugate. Okay, complex conjugate of these numbers. Okay. So this is the inner product of pi and psi. Okay, so we have a Bra psi and Ket Bra pi and Ket psi. Okay, so in this product, in this inner product, we take the column vector and converted that column vector as a row vector. Okay, so first we take the Ket psi, Ket pi, okay, 2 6i. So that is converted into a row vector. Okay, so I take 2 minus 6i. Minus 6i is a complex conjugate of 6i. Okay, then I take psi. Okay, so the multiplication of this one is 6 minus 24i. Is it clear?
Yeah, ma'am, it's
Yeah. Okay. Okay. Then we go for a tensor product of pi and psi. Okay. So 2 6i tensor 3 4. Okay. So we take the Ket pi and Ket psi. Okay. So this is useful. Tensor product is very useful in quantum circuit design. Okay. So the result is 6, 8, 18 I and 24 I. Okay. So this is an example of complex conjugate and transpose of a matrix A and Hamiltonian conjugate matrix of E. Okay. Okay. So next is a state representation of a quantum. So this quantum states are represented using a vector. So vector represents the quantities and with the magnitude and direction. Okay. So any state in quantum computing psi can be represented as a Ket psi equal to alpha A Ket 0 plus B Ket 1. Okay. So Ket 0 can take this vector value 1 0, 1 is 0 1. Okay. So other than that, we have this cos theta by 2 0 plus sine theta by 2 e power I psi 1. Okay, so this is another representation of quantum state. So the normalized state will be norm a square plus norm b square equal to 1. So this is from our bound rule. Okay, so these are very useful in measurements. Okay, I skip this. Okay, so in quantum mechanics, we have key concepts like wave particle duality and superposition. Then we have uncertainty principle and entanglement. Okay, so superposition and entanglements are key concept in quantum computing. They are useful in algorithms also. Okay, so the superposition is represented like this. So we have a Q0. Okay, so that is taken as a 1 by root 2 I by root 2. Okay, the superposition of this bit can be written like this: 1 by root 2 ket 0 plus I by root 2 ket 1. Okay, so for example, this we have a ball and box. If the ball is outside the box, it is represented as a 0. It is inside, it is represented as a 1. Okay, ket 1. If it is in both state, the state will be a superposition state, that is represented as a ket 0 plus ket 1 by root. Okay, so the superposition state is not entirely 0 or not entirely in one state, but the linear combination of these two states. Okay, okay, we have a computational states basis states for quantum computing. We have a z basis, x basis and y basis. In z we have ket 0 and ket 1, then x plus and minus, ket plus and ket minus, and y we have a r and n. Okay, so in z basis we have a 0 and 1, then y basis we have a plus, that is represented as a ket 0 plus ket 1 by root 2, and minus state is represented as ket 0 minus 1 by root 2. Okay, and we have a y basis. Here we have a I. Okay, so r equal to ket 0 plus I ket 1 by root 2, then ket L equivalent to ket 0 minus I ket 1 by root 2. Okay, so this is a block square representation of these three states, basis states. So north pole represents 0, south pole represents 1. Okay, we have a x and y. Okay, so x for x we have a plus and minus, for y we have minus plus I and minus I. Okay, okay, so this for a multi-qubit system. If I have a more than one qubit, I can represent like this. Any size state for a multi-qubit system can be alpha ket 0 0 plus beta 0 1 plus gamma 1 0 and okay.
Yeah, ma'am, there's one doubt. Somebody asked, is tensor product and outer product are same?
No, sir.
Yeah.
That is different.
Yeah.
So in so this is a tensor.
Yeah.
Below is a tensor product, above is a dot product, inner product. So in inner product, we take the dot operation, that is a normal matrix multiplication. But for a tensor product, we do like this. Okay.
Right. Even it will be like in tensor product, it will be 4 cross 1. Like we can see the example, like this 2 and 6i, then 3 and 4.
Yes.
Then it will be 6, like in
Yes.
the end 4 cross 1, right? And for
Yes.
outer, it will be like 2 cross 2
2
matrix only
plus
for
1.
out.
Yes.
Okay. Another doubt was why theta by 2 instead of theta in the state representation.
Okay. It's not clear, sir. What is it?
Okay, then one is like, yeah, we will share the slide at the end of the session, don't worry.
Okay.
We will call z basis as computational basis, or we can call x and y also.
We have 3 basis states in quantum computing. So normally we do the operations on as z basis.
Yeah. Okay, ma'am. No, there's no other doubt.
Okay. Okay. So single qubit gates, we have Pauli gates like X, Y, Z. Then we have a Hadamard gate and P gate, IST gates, and we have a general U gate. Okay, so these are a single qubit gates because these are operated on a single qubit. Okay, so first one is X gate. This is like our NOT in classical. So it operates on a single qubit. So when I apply Ket0 on X, it converts that state into 1. Okay, Ket1. When I apply 1 on X, it converts into 0. Okay, so in quantum computing, all the gates are represented as a vector, that is matrix. So this is a matrix representation of X. So X equal to 0, 1, 1, 0. So this is circuit representation. So single qubit takes X gate. Okay. So this is a simple matrix multiplication operation. So see this example. So if I have a 0, get 0. So we take the column vector of get 0, 1, 0. So X on 1, 0 gives matrix, we take the X matrix into 1, 0. So after multiplying, I get 0, 1 as a result. So 0, 1 represents 1 stick, get 1. Okay. So if I take 1, get 1, this is 0, 1. So X matrix into 0, 1, that is 0, 1, 1, 0 into 0, 1, it gives 0 dot 0 plus 1 dot 1, 1 dot 0 plus 0 dot 1. So 1, 0. So 1, 0 represents get 0. Okay. So X gate is like our NOT gate in classical. So X on 0 converts 0 state into 1. So X on 1 converts our 1 state into 0 state. Okay. Next is a Y gate. So this is also act on a single qubit. So this notation that if I take a 0, so when I apply 0 on Y, it converts it into I1, get 1. When I apply 1, it converts it into minus I, get 0. Okay. So this is a matrix representation of Y. Y equal to 0 minus I 0. Okay. So this is a circuit representation. Okay. So this is a Z gate. So this is a matrix representation 1, 0, 0 minus 1. it also performs the rotation pi around the y-axis and z-axis of the block sphere. Okay, so when I apply 0 on mm, 0 on z, so there is a no change in that state. Okay, when I apply 1 on this, it converted into -1. Okay, it only changed the phase. Okay, plus is converted as a minus, plus converted as a minus I. Okay. Okay, we'll move to the hands-on session. So open your IBM Composer, Quantum Composer.
Yeah, so you guys can join with your phone and use your laptop or just do somehow. And we are going to execute the basic gates. Hi, Karthik sir. Hi, KG.
Hey, good evening. Please continue. I joined as an audience only. Go ahead.
Okay, good to have you. So, yeah, man, continue.
Okay.
Or maybe they can watch now and they can execute later, like they can understand how things are going on.
Okay.
Then they parallelly, yeah, it depends on them. Yeah, and you can start.
Okay. So search for IBM Quantum Composer. So go to this link, IBM Quantum Learning. So it gives Quantum Computer Composer. Okay.
Yeah,
IBM
somebody was asking, he has VS Code and don't have, so you don't need to have this like software. It's a website and you can directly search on Google and you can join. Yeah.
Okay. If you want, you can sign in with your Google account, or you can create a account in IBM Quantum. Okay. Okay. So now we have a single qubit. So I delete all these qubits. So I have a single qubit and a single classical bit. Okay. So before that, you should know all the qubit is initialized with 0 state initially. Okay, so Q0 is a 0 state. Okay, so when I apply X on this, so this is a X gate. You can simply drag and drop. Okay, X on this. What is my output? See this histogram and Q sphere representation. Okay, so the probability of 1 is 100. So my output is 1. When I apply X on 0, my output is 1. Is it clear?
Yeah, ma'am, they are allowed. They can't unmute, but
Okay.
they can. Yeah, you guys can type on Q&A that you can like write the answer there,
Okay.
or yeah, you can read thumbs up or something like that.
Okay, so this is a Q sphere representation. In Q sphere, we have a block sphere representation and Q sphere representation. So here we have a Q sphere representation. This south pole represents 1. In Q sphere also, the south pole represents 1. Okay. So if I need a 1 state in Q0, I simply apply this X on Q0. Okay, so it is in one state. So after that, I apply X gate on this. What is my output? Output is 0. Okay, so output is 0. Why we have two X's on this Q0? To make this Q0 as a one state, as in one state. Okay, so this is a X gate. Okay, so then we go for Y. Okay, so 0 on y, it is 1, but the phase changes reflected in this Q sphere. Okay. Okay. 1 on y. So this is 0. Okay. Then we have a z gate. Okay. So no change for 0 state. So my output is 0, again 0. So when I apply 1 on z, so my output is 1. So it is in -1. So the Q sphere line is in red color. Okay. So this environment is easy for understanding the operations of quantum gates. Okay. We can also have the code for this circuit at the right side. This by default it is in some code. If I want, I can convert this as a Qiskit code. Okay. I can also download this. I can also export this circuit.
Yeah.
Okay.
So this is
So,
basically drag and drop, like somebody, like the one who are starting and learning quantum computing and they want to implement gates. So without coding also, like this is drag and drop, like ma'am showed. Like you can execute all the gates, Hadamard gate. But later on, like we will need some coding stuff. But you can see as in like side, like the right side, you have option to, the code is also there. So you can copy this code and try to execute. And maybe in the end, we will show, like I will show how we can implement by coding also in VS Code. Yeah, ma'am, continue.
okay. So that's all about Pauli gates. Then we go for H gate, Hadamard gate. This is an important gate in quantum computing because it creates the superposition in quantum computing. Okay, so this matrix representation of this H gate, H equal to 1 by root 2, 1, 1, 1 minus 1. Okay, so Hadamard gate creates the superposition of 0 and 1. When I apply 0 on H, it converts it into a plus state, kit plus. Okay, so kit plus equivalent to 1 by root 2 of kit 0 plus kit 1. Okay, when I apply uh, 1 on H, it converts it into minus state. So that is equivalent to 1 by root 2 of kit 0 minus kit 1. Okay. So these are some.
Somebody asked another one doubt, so I will take that. Like somebody asked, like I would like to ask that can we run this program in VS Code, or is it can only be run in IBM Quantum? It can be like for a demo purpose, we can use IBM Composite. Later on, we can do the same thing on VS Code as I already mentioned. So it's not mandatory. Like it's like as you mentioned, like can it be only run on IBM? It's not like that. It can run on Jupyter also, Google Colab also. So we,
Okay.
yeah, okay.
I can give a demo on this. So again, we go for Composer. Here I delete these gates.
Yeah, now
Okay.
it is like all with coding. This is
Okay.
Hadamard, yeah.
H. So 0 on H, it creates the plus state. So the probability of 0 and 1 states will be 50-50. Okay. 0 state gets 50% and 1 state get 50%. So this is a superposition state. So in Q sphere, we can see 0 and a line which connects 0 and 1 state. both 0 and 1 state in Qiskit. Okay. So when I apply 1 on this H, okay, so the only change in minus get 1, 0, get 0 plus get 0 minus 1 by root 2. So the one in Q sphere, the one state is in red color. Okay. So that's all about H gate. So it creates the superposition in quantum. Okay. Then we have a P gate. I is the identity gate and S gate. Okay. Then T gate and U gate. Okay. So this is a summary of single qubit gates on different states. Okay. So the plus state represented like this: 1 by root 2, get 0 plus get 1. Minus state is 1 by root 2, get 0 minus get 1. Then I is 1 by root 2, get 0 plus I get 1. Then minus I is 1 by root 2, get 0 minus I 1. Okay. When apply x 0 on x, it converts into 1. 1 on x is 0. X on plus is plus. X on minus is minus minus. Get minus. Okay. X on I is I, then minus I. X on minus I equivalent to minus I get I. Okay. Then y on 0 is I1. Y on 1 is minus I get 0. Y on plus is minus I get minus. Y on minus equivalent to I get plus. Then y on I is I. Okay, get I. So y on minus I equivalent to minus minus I. Okay, when I apply 0 on z, there is a no change. My result is 0. So z on z on 1 is minus 1, plus is minus, minus is plus. Then z on I on z equivalent to minus I, then minus I on z equivalent to get I. Okay, so h on 0 gives plus state and h on 1 gives minus state. Okay, get minus. Okay, we should know this, then only we can design a circuit. So we have some rotation gates, rotations. Okay. Okay, so multi-qubit gates. These gates operates on multiple qubit, more than one qubit. Okay. If I have a 2 qubits, the possible states are 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So this is a CNOT gate. So this is a control NOT gate. Okay, it operates on 2 qubits. Q0 is a control qubit. Q1 is a target qubit. That is mainly used in entanglement. Okay. Combination with H gate, we can create an entangled state. So this is a gate picture, gate diagram. So Q0 is a control qubit. Q1 is a target qubit. Okay. So it means that if Q0 is 0, there is a no change in Q1. If Q0 is 1, there is a change in Q1. That is, it flips the state of Q1 if the Q0 is 1. Okay. If the Q0 is 1, there is a no change in Q1 state. If Q0 is 1, it flips the state of Q1. Okay. Is it clear? So this is a matrix representation. Okay, generally we follow two representations. Okay, so 1000, 001, 0010, and 0100. Okay, another representation is 1000, 0100, 0001, then 0010. Okay, so this is a table for input and output. If my input is 0 0, that is target and control are 0 0, my output is also 0 0. If my control is 1, my target is 0, the output is 1 1, because the control qubit is 1, so it flips the state of the target qubit, so it converts that 0 into 1. Okay, so that we have a x on this q1. Okay, if the x operation on q1. Okay, so next 1 0, control is 0, so the output will be 1 0. Next input is 1 1, so the control qubit is 1, so it flips the state of the target qubit, so it is 0, so the my output is 0 1. Okay, so we move to the
Yeah, there was one doubt like about the matrix. Can you
yes.
again? Yeah, can you just slide show this?
Yeah. Okay.
So why it is different? Like they were asking like why it is different. So it basically depends. Like what I feel is like why it is different, because suppose if you take like this 0 0.
0 0 0
If
1
you
1.
like, it depends on you from which like which side you are starting. Like
Start.
if I'm starting from left side, and then it will be control bit, like suppose for the first one, 0 will be control, and 0, that's right side will 0 will be target. So if control is 0, we don't do any change. If control is 1, then we flip it. Now
Yes.
reverse it. Now reverse it, you will get the different matrix. And the one somebody asks like how to get this matrix, just basically draw, like suppose just give the number 0 0, like just keep on giving the column name 0 0 0 1 1 0 1 1, then the row wise, and then assign the values. If 0 0 and 0 0 1 is there, then try to put 1. Then second one is 0 1 and 1 1, try to match. So suppose 0 0, then 1 1 is there, then you have to match it. See, it is there. And 1 0, then 1 0 is here, and 1 0 will be here.
Yes.
Then 1 1, 1 1 is last, and 0 1 is here. So if you will reverse it, then second matrix will come. So yeah, so that's why they are getting confused. Yeah, but it's easy to implement.
Okay.
Yeah, ma'am.
Okay. So we need 2 qubits. So I increase the qubit number. So we have a CNOT. Okay. So here I have 2 qubits. So the possible states are 0 0 0 1 1 0 and 1 1. Okay. 0 0 0 1 1 0 and 1 1.
Because nothing is there, because there's 0 control and 0 target. So it will be same. And now can you just use some Qiskit?
X.
Now, yeah, ma'am, go on.
The output is 1 1. Okay.
Because like first 0 will Q0 will convert it into 1, then control will be 1, and second one is 0 already, because there's nothing and there's no Qiskit. So 1 will flip. So 1 will flip it to 1 will remain same 1, and then 0 will be flipped to 1. So it will be 1 1. So you can see the graph also here. Yeah. Yeah, ma'am.
Okay. So we get the combination of these two qubit states as out. Okay, 0 0 0 1 1 0 and 1 1. So here our output is Q0 is one state, and Q1 is also in one state. So the output is 1 1. Okay. So that, so like that we have C is a gate. So this matrix representation 1 0 0 0 1 0 0 0 0 1 0 0 0 minus 1. Okay. And we also have a swap gate that is mainly used for interchange the states of Q0 and Q1. Okay, so this matrix representation swap gate 1 0 0 0 0 1 0 0 1 0 0 0 0 0 1. Okay, so next one is very important gate, CCX gate. It operates on 3 qubits. Okay, so this is like our CNOT gate, but here we have a 2 controls. Okay, 2 control qubits and 1 target qubit. Okay, so here if Q1, Q0 and Q1 are in one state, it flips the state of Q2. Okay, so this matrix is like this. If both the controls are in state 1, it flips the state of target qubit. This is a Toffoli gate. Okay, so that's all about the multi-qubit gates. Okay, so these through these gates we can design a quantum circuit. For creating an entanglement, we need a H gate and CNOT gate. So these are the 4 different entanglements. This is known as the Bell states. So pi plus, pi minus, psi plus, psi minus. Okay. If both the qubits are 0 0 plus 1 1, then it is known as the pi. If it is different, it is known as the psi. Okay. So kit 0 0 psi plus is kit 0 0 plus kit 1 1 by root 2. Pi minus is kit 0 0 minus 1 1 by root 2. Psi plus is 0 1 plus kit 0 1 plus 1 0 by root 2. Psi minus is kit 0 1 minus 1 0 by root 2. Okay, so this is a Bell state. So this is a circuit for the Bell state. Okay. So in Composer we can do. So we need a CNOT and H. Okay. So it creates the entangled state. So 0 0 50%, 1 1 50%. Okay. So this is an entangled state. Because H creates the superposition on Q0. So when I apply 0 on H, it converts that 0 into plus state. So plus equivalent to get 0 plus get 1 by root 2. So when I apply that on C0, it converts that state into 0 0 plus 1 1 by root 2. Okay.
Yes.
So when I apply 1, so the minus is represented like, so in Q sphere you can see the phase change. It is in red color. Minus 1 1. Get 0 0 minus 1 1 by root 2. When I apply 1 on H, it converts it into minus state. Get minus. Okay. When I apply C0 on H minus, so get minus, it is in get 0 0 minus get 1 1 by root 2. Okay. Okay. So like that we can create this X H and C0. So if it is in this position, it creates 0 1 plus 1 0. Okay. Then okay, so this is minus 0 get 1 0 minus 0 1 by root 2. Okay, so these are the four states, four entangled states, four different entangled states. Okay,